Alright, so this module is talking about basic diode circuits. We're going to look at an example of a diode in a circuit and see how we analyze that circuit using nodal analysis, and we're also going to look to see if we make the wrong assumptions about if it's forward biased or reverse biased, what that means to our circuit. So first off, remember forward biased. There's some things that we have to remember about a diode. In the forward bias, if it's forward, it means that current is going to flow through it. And that also means that the anode, that side of the diode is the anode, is going to be 0.7 volts is an approximation that we use. It's not exactly it for every diode. It's different. In fact, it's different for every diode, but we're going to say 0.7 for our purposes. It has to be 0.7 volts more positive than this side. So if this is grounded, for instance, and it's forward biased, we know that the voltage here is going to be 0.7. Or if we know that there is 10 volts here, and we know that this is forward biased, we know that there has to be 10.7 volts there. Now for a reverse biased diode, if it's reversed, well, that means that no current is going through it, that the current's going to be trying to go through it that way, but it's blocking it. I think the symbol was designed to tell us what was going on, so the arrow points that way, meaning current can flow if the current's that direction, but the flat line's blocking it like a wall, so it's blocking it right there if it's heading that direction. Okay, so let's put that into a circuit and see what happens. We'd make up any old circuit. Let's say we have a power supply, and we'll make a little circuit that has a node here. Ground that and ground that, and we'll put another node here with a diode in the circuit. One thing that you might note is that I put the resistor before the diode. In that branch, our circuit analysis won't change if we put the diode before the resistor after the diode. It doesn't matter. One way or another, it's the same. So let's add some values here. Let's say that's 5 volts and 1 kilo ohm. And just to be different, let's say 2 kilo ohms and how about 3 kilo ohms. There we go. So the first thing, when we get a circuit like this, we have to figure out what the biasing of this diode is going to be. Now you can't know that beforehand, or not easily. So what we're going to do is we're going to make an educated guess. We know that current's flowing this direction through it, so my guess is that current's going to flow here, it'll probably break off and go that way, and that there will be current flowing that direction, and that is the proper direction for forward biasing. So I'm going to guess that this is forward biased. And we're going to use that assumption and solve this circuit and see what happens. So just like any Kirchhoff current law using nodal analysis, we're just going to find label the currents in each branch of the circuit. We'll just call it I1, I2, and I3. And we need to solve for those currents. So let's do that. So we say I1 is equal to I2 plus I3. That's just Kirchhoff's current law. The currents into the node is equal to the currents leaving the node. And then we need to set up some equations, some other equations. We have 3 unknowns, so we need at least 3 equations. So let's see what we can do. I bet we can come up with 4 equations. We can say I1 is equal to, well, it's going to be the voltage drop across this 1K resistor. What's the voltage drop? We don't know, but we know that what the voltage is here, and we know that there is some voltage there. So we're going to use that knowledge and say that this is 5 volts minus Vn divided by 1K, and that's going to be our current. It's 1 kilo ohm resistance. I2 is just equal to Vn over 2 kilo ohms, and I3 is equal to Vn over 3 kilo ohms, but that's not complete, because remember up here there's a 0.7 volt drop. So we know that this voltage here is 0, and so this voltage here has to be 0.7 volts. And so the voltage difference isn't going to just be Vn to the ground, it's going to be Vn to 0.7 volts, so it's Vin minus 0.7. And so we have four equations. We're just going to take these three equations and plug them into the Kirchhoff's current law equation and come up with a big equation that we can solve doing the algebra, if we can do it properly. So let's write that equation. I1 is just 5 volts minus Vn over 1 kilo ohm, and that's equal to Vn over 2 kilo ohms, and that's plus Vn minus 0.7 over 3 kilo ohms. So I'm going to skip a bunch of steps here and write this out as 5 volts is equal to Vn times, let's see, we got 1/2, we got 1/2 plus 1/3, and I move this over here, so plus 1. You notice I divided everything by both sides by 1 kilo ohm, and then I combined all my Vn terms, and that leaves me with minus 0.7 volts, so volts, divided by 3. And so we're just going to add that over here. We punch that into our calculator, and we have 5.233 volts is equal to Vn times, and that is 1.83. We just added that to the other side, and so we divide both sides, and we have Vn is equal to 5.233 divided by 1.833, and that should equal 5.233 divided by 1.833. What did that? It is equal to 2.854. So now we have the voltage for Vn, and we can go back and plug this back into our equations. So we're just going to plug in everywhere in these equations that we had Vn. We're just going to plug in 2.854. And so, for instance, up here, we're going to do that, and you get 5 minus 2.854, and I divided by 1 kilo ohm is going to be I1 is equal to 2.145 milliamps, and I2 is just 2.854 divided by 2 kilo ohms, so it's 1.427 or something like that. 1.427, and I3 is equal to, we'll just do this one real quick on the calculator, 2.854 minus 0.7 divided by 3 is 0.718 milliamps. And so if we add those up, we get 21. So it looks like our math worked out. We can see I1 is equal to I2 plus I3, and that's going to roughly be about right. So that's how it looks whenever you do it right. Now what happens if we made the wrong assumption earlier on in the circuit, and we said that it was reverse biased? Well, let's see. So if we change this from forward to reverse, now there's no current flowing in this whole branch, so our equation here, I3 is going to be 0, and so it's just I1 equals I2, and I3 is equal to 0. So if we do that, well, in fact, we don't really even have to do the math. We can figure out what that current is. That's going to be I1 and I2, and since there's 0 volts here, we know that Vn is going to be some number. That's just the voltage divider. 2 divided by 3, so it's 2/3 of 5 is what Vn is going to be. And what is that? 5 times 2 divided by 3 is 3.33 volts. So Vn is going to be 3.33 volts if this is reverse biased. But because there's no current flow here, that means that there's no voltage drop here, so the voltage here is no longer 0.7, it's 3.33 volts. Well, if you have 3.33 volts here and 0 volts here, that means that you have a larger than 0.7 volt drop across that diode, which is not possible. That it can only be 0.7, or it can, or it has to be, the current has to be flowing the other direction. And so if the current's not flowing the other direction, and we have this bigger voltage here that goes like that, that obviously means that we've done something wrong. Alright, so now let's try it one other way. Let's redraw the circuit. And say we have, instead of, I'll try to draw it fast here. Instead of 5 volts, let's say we have negative 5 volts. 1K, 2K, and 3K. And let's say that we assume that it was forward biased this time, because that's the real question. The reverse biased, if the current, if the current is, we can see which way the current's going, and it's obviously going this direction, and it's more than 0.7 volts, then we know it has to be forward biased. If it's flowing this direction and it's less than 0.7 volts, then it's reverse biased. But anyway, let's look at this circuit here. 0.5 volt, or negative 5 volts, and we do the same thing. We say it's forward biased, so we work through the whole thing again, and we say I1 equal to I2 plus I3, and we I1, I2, and I3, where I1 is minus 5 minus Vn divided by 1K, and this one is Vn divided by 2K, and this one is Vn minus 0.7 divided by 3K. Okay, so we have our circuit equations there. We can plug them in, start solving, and we have minus 5 minus Vn divided by 1K is equal to Vn divided by 2K plus Vn minus 0.7 divided by 3K. And we'll do a little algebra here, and we will have minus 5 is equal to Vn 1/2 plus 1/3 plus 1 minus 0.7 divided by 3. And so we add this to this, and this time this is going to be negative 4.76. I said 76, but I drew a 4. 4.76 is equal to Vn, and we can just divide that by 1.833. So now this equals, we just do a little calculator here, negative 4.76 divided by 1.833. It's negative 2.6. So negative 2.6. Now we go to plug these things back in, and what we're wanting to look for is, because we said this is forward biased, and we use the assumptions that the currents were flowing this direction. That's what we said when we said I1 is equal to I2 plus I3. We made some assumptions there. We said that the current's flowing this direction, and that's the currents into the node, and those are the currents leaving the node. Alright, so that's how we set up our equation. Now we look at this and we say, if this one says it's going that way, if the current says it's going that direction, then we know it's obviously wrong, that has to be reverse biased. If we get a negative current over here, then it has to be wrong. We could have made an assumption that the arrow was pointing this direction. If we make that assumption, we've made contradictory assumptions then. We've said that this is forward biased, but the current's going the wrong way. So we expect a negative number in that case. But in this case, where we made an assumption that this is forward bias and this is going this direction, we want to make sure that the assumptions match up, which means that the current will be positive. So let's see what happens here. And we can skip, we found Vn, so we can skip I1 and I2 for right now and just go straight to I3 and solve for that and see what it looks like. And whenever we do that, we just have a negative 2.6 minus 0.7 divided by 3k, and so we have a negative 3.3 over 3k, and you can immediately see that it's a negative voltage, and that means that the current is trying to, a negative current, I said voltage, that's a negative current, and so that means that the current is trying to go that direction, which is obviously incorrect. If you ever end up with a circuit with your current flowing that direction, you've done it wrong, which means you have to pay close attention to the signs in your equations and make sure you understand what your assumptions were in the beginning. And that'll do it for now.